It's a complex beast, and in order to break it down we need to get to grips with two concepts, one of which is fairly straightforward, surface temperature of a star, and the other which is a little bit more involved, the luminosity of the star. I still find it almost impossible to believe that the tiny amounts of light that arrive on planet Earth from stars, if handled correctly, can lead to so much information about the stars from which they came. For example, if you can capture this light and shine it through a prism, you can split the light into its component colours, and then, unbelievably, you can measure the intensity across the whole spectrum. If you do this, you usually find there's some kind of peak value for wavelength. Then, using Wein's law, because we consider stars to be perfect black body radiators, we can then get a value for the surface temperature of a star. That's awesome. The luminosity of a star is not really the only factor that affects how bright a star seems to us. In fact, the luminosity is a measure of how much energy per second is leaving the surface of the star. So in other words, it's like a power. And as you can imagine, it's normally a pretty enormous number. The x-axis of the Hertzsprung-Russell diagram is usually pretty straightforward. It's temperature measured in kelvins, but it's kind of round the wrong way, and it also covers a huge range. So on the left hand side we'd normally sort of start with 50,000 kelvins, i.e. flipping hot, and then on the right hand side go across to the lowest temperature around about 3,000 kelvins, which is still pretty hot. The y-axis is more variable. Most of the syllabuses in the UK talk about relative luminosity. This is where you set the luminosity, remember the power output, of our sun and call it 1, and then you compare all the other stars on the chart to the value for our sun. There are a huge range of values you can have here, so the y-axis in this case will go up to about 10 to the power of 6, all the way down to something incredibly dim, 0.01 times the luminosity of our sun. It's normally therefore a log axis. Since astrophysics is an option for our friends at AQA, and since they like to always go a bit further if they can, they've replaced the y-axis on the Hertzsprung-Russell diagram with absolute magnitude. Absolute magnitude really is a measure of how bright something appears on the Earth if you put it at a standard distance, this distance being 10 parsecs. Therefore we can compare the brightness of every star because they're all at the same distance. It's a weird old axis though, because it peaks at -10 and its smallest value is +15. We'll just leave it there for now. If you gather data for thousands of stars and plot their surface temperature against their luminosity, you find a very clear pattern emerges. There's a sort of long thin thing that goes from very hot and very luminous down to quite cool and very non-luminous. This is called the main sequence, and it's where stars spend most of their lives. Our sun, or Sol, to give it its proper name, is here, at a luminosity of 1, as you'd probably expect. Up in the top right corner is an oval shape where the red giants and the red supergiants live. Some versions of the Hertzsprung-Russell will show this as two separate areas. In the bottom left-hand corner is another oval where the white dwarfs live. Stars form in great big dust clouds. These dust clouds are primarily made of hydrogen gas. Areas of this cloud collapse, and as they do so, under the force of gravity, the cores of these kind of spheres of gas will begin to warm up. Eventually the temperature of the core becomes so hot that nuclear fusion can start to occur. And now photons with great amounts of energy are coming out of the star. So we have an outwards force called radiation pressure caused by the photons from fusion and an inward force from gravity, and these two forces balance and we now have a stable position. The star is born and joins the main sequence. Most stars will spend a long time living, as it were, in the main sequence. How exactly they progress in the main sequence and how they leave it depends very much on their mass. The different syllabuses treat this very much in different ways with different bits of detail. I'm going to keep it simple and just consider the basic process for a star that has a mass of less than 10 times our sun. These stars will spend a long time in the main sequence in a state of equilibrium, gradually warming up, becoming a little bit brighter as they burn up, burn being the wrong word of course, their hydrogen fuel in their cores. Eventually we reach a point when the core hydrogen begins to run low. This means that the pressure outward starts to drop. The inside of the star, or the core if you like, starts to collapse, and at the same time the outer layers start to move outwards. The star is becoming much bigger and much cooler, and is in fact becoming a red giant. This means that on the Hertzsprung-Russell diagram it moves up to the top right area. When a star moves from one part of the Hertzsprung-Russell diagram to another, it does so very quickly. I mean, it might still take hundreds of years, but then for a star, that's just a blink in an eye. The red giant in its core is primarily using nuclei of helium to fuse together to form carbon and oxygen, producing lots of energy which maintain or push out the layers a long way. This is why it's cool on the outside. Eventually though, the supply of helium nuclei within the star will begin to run relatively low, and so the star's core will begin to collapse again. At this point the star sheds or throws off its outer layers completely in what's known as planetary nebulas. These are basically clouds of dust and gas, and these just fly out into space and can contribute to the birth of new stars later on. Astrophysics for me has always been one of the most interesting areas of physics. When a red dwarf sheds its outer layers into a planetary nebula, the object left behind is a fascinating, very small, very dense object known as a white dwarf. In fact, it's so dense you can consider it to be a solid. These white dwarfs, therefore, are right down on the bottom left-hand side of the Hertzsprung-Russell diagram. So they have low luminosity but really high temperature. That's because they're so small. What happens to white dwarfs as time goes on is they simply just cool down, and eventually they disappear as they become cold and dark. I always think this is rather a sad ending for a star, really. As I've explained, there are different endings that can happen for a star and some truly fascinating objects to deal with. I decided to keep things simple in this video because really it's about the Hertzsprung-Russell diagram. There are many other interesting endings for the life of a star. Perhaps we'll do a video on those too. If you found that video interesting, why not try this one?